to this new course unit, which is nothing more than a branch of electrical engineering that deals with having specialized computers, tiny computers that have specific tasks in the real world. Unlike ordinary idea of a computing system whereby it can do a number of tasks, unspecified number of tasks, even when, let's say, you're buying a computer from an electronics store, right, or shop. You'll find that you're buying a laptop, let's say a laptop computer to do video editing. Someone could be buying a laptop to play video games, to run a business by running, let's say, a supermarket software package, anything generic, right? So as it turns out, electrical engineering has a branch of electronics called embedded systems. So embedded systems is comprised of specialized computers designed to perform one specific task inside a large device, let's say such as washing machines, traffic light control systems, smart meters, and so on and so forth. So let's look at a basic structure of an embedded system. So to visualize what I've just described, this is how it would look like. So we have a basic structure of an embedded system. It's comprised of three major parts. I repeat, it's comprised of three major parts. So we have what we call the sensors. We have sensors. So sensors are nothing more than circuits that change their behavior, their electrical characteristics, that is voltage or current or both, due to a change in the physical parameter in the real world. Let's say, for example, we have what we call a temperature sensor or a light sensor. For a temperature sensor, this is a circuit whose output voltage or current or both change when there is a change in the environmental temperature around this circuit or sensor. So if it was a light sensor, it would be a circuit whose output parameters, for clarity, let's just say voltage, whose output voltage changes when there is a change in the ambient light. So if, let's say, the light levels go high, you would find that a certain sensor changes its output voltage linearly to the change in light levels. Let's say if the light levels increase, you will find if the light levels increase, you will find that if, let's say, the light levels increase, you will find that the output of that circuit we are calling a sensor is also increasing in response to the increase in light levels around that sensor. You get the point? So that's what a sensor is. We could have sound sensors, we could have magnetic field sensors. So a sensor is nothing more than a circuit whose output changes, whose output parameter changes. One of its parameters, it could be voltage or current, changes when there is a change in the physical parameter, like temperature, weight, magnetic fields, light. You get the point. So when there is certain change, this circuit detects a change. What happens? So now let's say we have this block representing our sensor or sensors, and like we will see in the real world. So that information, that change, is being detected by a circuit called a microcontroller. This is the specialized computer designed to perform one task inside a larger device. This is it, what we call a microcontroller. And it's not only a microcontroller, as we will see, because sometimes we have a microprocessor, sometimes, but most likely this is the architecture. So big picture wise, we always have sensors or a sensor. We have a device to process. So this processes input, what we call input, right? This processes data. This processes data. This processes data. So this microcontroller processes data. So for example, in this course unit, we are going to be dealing with the Atiny 85. So this is our example. So there are very many microcontrollers on the market. There are very many microcontrollers on the market. There are very many microcontrollers on the market, right? So you will find that there are microcontrollers made by different vendors like PIC microcontrollers, STM32 microcontrollers, ESP32, Atmel. There are very, very, very many. So to make this course unit more interesting and easy to follow along with, we've chosen to go with the Atiny 85. So the Atiny 85 is nothing more than a microcontroller. So it's a specialized computer. That means it can run a program. Remember, the basic characteristics of a computing system comprise of the following. A computing system must be able to take inputs, both analog and digital, process that information, then give an appropriate, meaningful, related output. I repeat, if you remember, for those who took computer classes in your previous levels of education, that is in high school, primary section, even at home. So I'm quite sure you've ever come across a statement that says a computer must be able to take input, process inputs, then give us an appropriate, reliable, and related output. So in this case, what comes in as the sensor information? What comes in as the sensor information is processed by a computer. So in our case, our computer is a microcontroller. Remember what we need to have a computer. What we call a computer, we must have a CPU and ALU on the inside. Now I'm describing what we will find on the inside of a microcontroller. We may have, most likely have, a central processing unit, that is one. We have an arithmetic logic unit, ALU, and registers that make up different other sections of a computer, the memory, the RAM, everything. So communication. So all of it is comprised in this one part. All of it is comprised in this one part. So you get the point. All of it is comprised in this one part. So let's say now we want to implement something. Let's say if temperature, let's say if we have a temperature sensor as our input to a given microcontroller, which is at the Atiny 85. So you can look up the Atiny 85 on Google. You will have a lot of information given to you about this microcontroller. It's an interesting microcontroller. It falls in the family of the AVR microcontrollers. So, and it's an 8-bit microcontroller. So we'll look at the details later. So let's say we have a temperature sensor, right? So this temperature sensor is going to help us do the following. Let's say now it's bringing in temperature information about, let's say, temperature information of a room, let's say in our lecture room. And the lecture room, let's say after lunch, tends to get hot. And we have a microcontroller to process this information, then make decisions upon it. I will explain the decision part. I will explain the implementation part. Then we have what we call actuators. These are other circuits, systems. They could be electrical, they could be mechanical, most likely a combination of both, that implement a specific task with the one we were talking about right from the beginning of the lecture. So remember, we said an embedded system is a specialized computer designed to perform one specific task inside a larger device, such as a washing machine. So in this case, we have a temperature sensor. That is the input part. The processor part, we've said we have the Atiny 85. Then on the actuator, we can have a fan. And the fan is nothing more than a motor with fins or propellers. So pushing air around. So you will find that, let's say we can set this to work to our advantage. Let's say if the temperature value exceeds a certain threshold, let's say room temperature, let's say 25 degrees Celsius, right? So the moment the temperature sensor gives the microcontroller information that the temperature in the room is exceeding 25 degrees Celsius, we can instruct, mark the word instruct, we can instruct the microcontroller to give specific actions. We can instruct the microcontroller to give specific actions, right? So actions like, in this case, run a motor. So in this case, if we have a fan as the motor, it will start spinning. It will start spinning, driving air around. So the air molecules keep on colliding and they lose energy, thereby reduce the temperature. So we've found a way to interface a circuit that changes when there is a change in temperature. We've found a way to interface it with the computing system, and we found a way to interface all of that with an ordinary motor or a fan for that case. So what is an actuator? An actuator is nothing more than a circuit or a system that implements a command. Most likely you will find a term called a relay. You will find what we call a relay. For those who have been in the field, who have been practicing with industrial installations and home automation systems, I'm quite sure you've ever come across the word relay. For those who haven't, it's just a circuit that relays a signal from a low power side to the high power side. So it's a switch. It's an electromechanical switch or electrically operated switch, most cases. So it could, an actuator could be an LED. Let's say you're charging your laptop. The moment you plug in the power cord, an LED starts flashing. That's an output. So it's giving a feedback back to the user in form of light. So that is an actuator. So this whole paradigm, sensors, processing, and actuation, that's what we call the basic structure of an embedded system. So let's talk more about sensors. So sensors detect physical conditions. The microcontroller processes information, and actuators perform physical actions such as switching a relay, turning on a motor or off. So I think this summarizes what I've been just talking about in the last 13 minutes. So this summarizes it very well. Sensors detect physical conditions, changes in physical conditions. The microcontroller processes the information. So information can be either digital or analog. We will look at this later on in the consequent lectures where we're talking about analog data and digital data. So that's interesting. So then, and the actuators perform the physical actions. They are the implementers. They implement a specific action, such as switching on a relay or turning on a motor. Let's say like in a washing machine, like we've had in our definition. Let's say like in a washing machine, right? A washing machine has a temperature sensor on the inside, right? Because it has to heat up water, right, to wash, to make washing process easier and faster. But the temperature of the water on the inside is monitored. And we have a spin drum, the one that spins. For those who have ever observed a washing machine in operation, it has what we call a spin drum. So the drum, or the washing drum, will spin, and it's attached. That means it's attached to a rotating device. This is nothing more than a motor. So the moment, let's say, the temperature goes higher than intended, blah blah blah, and other parameters, a motor can be stopped. It can be turned off. Otherwise the machine will never start or stop. So, and we have special controls for those who use very nice washing machines like those made by LG, Samsung. They have user interfaces. So this is an embedded system in action. It is helping us wash clothes. That is a specific task. So let's say for traffic light control, it is processing the number of vehicles on this lane versus that lane, how many it has released, for how long in this lane, on then the other route. You get the point. So that will be its information: number of vehicles it has let pass via a certain route within a specific time. That could be its input. And then the lights, the ones that we have, red, what, on the traffic light control system. It could be even giving other kind of lights to the pedestrians, right? To use the zebra crossing or the crosswalks, as you may choose to call it. So giving them a green light, displaying a countdown if you've ever witnessed how traffic lights work. So all of this is being ran by an embedded system. No one is going to be out there pressing buttons okay, like let this pedestrian pass. No, it's a preset system to follow a certain set of commands. We will look at the commands. We will look at that part later on. To perform a specific task in the real world. Okay, let me give you another example. Like, let's say smart meter. We have our metering devices, the ones that meter our utility usage, the ones that meter how we use utility resources, right? Utility resources like electricity. So for that case, the embedded system in big picture would, because instead of temperature, will be voltage and current, right? Instead of temperature and light, we could be collecting voltage and current values. So of a certain consumer. Let's say a homestead is operating at 240 volts. That's the voltage sensor giving us information. And the current at the moment is saying 18 amps or 10 amps or 5 amps, or someone is cooking, right? So the meter multiplies that and the number of hours you've been using that power, because voltage times current is power, right? In volt amps or watts, right? Depending on the kind of load you have. Then times the time, the duration of usage, that is the energy now. Those are the units. So those are the Yaka units we keep on referring to. So voltage, current, and duration, that gives us energy. So stored and communicated, blah, 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 blah. So that we have an actuator, let's say a relay. In this case, we have a relay in the energy meter, right? Our UEDCL meters or UMEME meters. I don't know how you choose to call them, but we have a relay to reconnect a consumer if they pay, if let's say they have a prepaid subscription, or their subscription expires. They've used enough, they've used all they've paid for so far, and it's time for disconnection. That's when the relay inside the meter unit disconnects the user until they reload again. Then the whole metering process repeats in a countdown fashion. So that would be a very good example of an embedded system. So hope I've explained the embedded systems paradigm, what embedded systems is all about. It's nothing more than grabbing a computing system, inserting it into an already existing system. It could be agricultural equipment, it could be electricity or utility measurement units, it could be vending systems, it could be transport. Like now we have electric vehicles, we have electric motorcycles roaming the streets of Kampala and all over Uganda. These are nothing more than embedded systems from the beginning to the end. Trust me, we will get to reveal more of what an embedded system is with real-world applications. So real-world applications involve transport, medication, security. Like now, guys, for those who are following, we have a current war going on in the Middle East, and countries no longer use spears to fight wars. war is not good, but it's part of society. So it's important to talk about it because embedded systems is at the heart and the center of this war, trust me. So these missiles that countries like Iran and Israel and other countries involved in this conflict are passing around, these are autonomously controlled, right? So these are computing systems that carry death. Sorry to say, but they have altitude sensors, the orientation sensors, temperature sensors, speed sensors. So these are embedded systems. So it's unfortunate they are used in a very, very unpleasant way, but embedded systems are used in security and military equipment, right? So transport, medication, entertainment. So we are all so much interested in content creation nowadays as young people, right? So you'll find people having devices like gimbals. You have tripods that keep on rotating around, so they are sensing orientation, they are adjusting, they are processing. So everything is getting smart and smart. So smart home systems, you'll find people bragging, I have an automatic opening gate. So, but this is just embedded systems on the inside. So in education systems, so you'll find that now, and this is very, very common now in international schools, international schools are tending away from blackboards and all this old fashion of teaching. Now people are using embedded system devices like smart boards and what to teach, right? To educate the masses. So the applications of embedded systems are very many. They are limitless. So the whole world is going to be evolving around embedded systems soon. So guys, you better pay attention and learn the course unit, right? So let's move on to the next piece of information. So like, remember I told you embedded systems are not only made of microcontrollers, but they are also made of what we call microprocessors. Advanced embedded systems, right? Intermediate to advanced. Beginner microcontroller embedded systems could easily only comprise of what we call microcontrollers. So it's important to know the difference between a microprocessor and a microcontroller. So a microcontroller is the basic form of a computing device, and it has all it needs to process on the inside, all in one construction, all on one chip, what we call a chip, all on one substrate, one chip. So when we look at a microprocessor, it's different in a way that it only has the basic processing unit, the CPU, the central processing unit, and nothing else on the inside, right? So it utilizes external, it utilizes external let's say it utilizes other peripherals connected to it externally. Let's say your laptop is a very good example of a microprocessor architecture. So it has, let's say, the Intel or M4, depending on the microprocessor you're using. Let's say using the Apple laptop, it could be the M series. If you're using Windows machine or Linux machine, most likely you're using Intel, right? So this processor relies on other external peripherals like the hard drive or the solid state drive, RAM, USB ports. Everything is connected to it via what we call data buses. If you've ever heard of that, we call them, these are just pathways to communicate, right? For the electronic devices to communicate. So it has devices, it has other external peripherals that help it implement display, audio, information transferring, processing, and storage externally. So that's why you will have people along Kampala Road selling hard drives, solid state drives to upgrade laptops and desktops. But a microcontroller has all it needs. It may be small, but it is all incorporated on the inside of the device. So let's just first go through this table, right? So it's comprising of features, so for the microcontroller and the microprocessor. So everything is integrated. So this is what we're saying. this is where we are saying everything is integrated. Integration, right? We have the CPU, the memory, and the input and output units, the ones that interface with the sensors and other devices, all integrated in one chip. So a microprocessor is a CPU only. So let's go to the power consumption. Now, power consumption of a microcontroller is very, very low. Let me give you a very, very good example of this. So our remote controls we use to watch TV, let's say in media, like I said, embedded systems is implemented in entertainment industry. So media, right? Multimedia. You're busy watching football at home and you're using a remote control to increase the volume, change the channel, blah, 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 so on and so forth. So you can operate your remote controller for months and months without changing the batteries, right? So what's on the inside of a TV remote is nothing more than a microcontroller and a couple of buttons or switches. So there it is nothing more than a microcontroller and an infrared LED to communicate the information you want every time you press a specific button. So, but this device runs on low power. That's why you only need two 1.5 batteries, right? Small AAA batteries that run for months without replacing them. So that tells us a microcontroller consumes low power, but a microprocessor, this one can drain serious power. Let's say your laptop can be, because it handles very many tasks as compared to a microcontroller. A microprocessor can have very many unrelated tasks running at the same time. So these tasks consume a lot of power. So you'll find that now modern laptops use, let's say 65 watts of charging. 65 watts charger, right? 85 watts charger. Now if you go to the gaming PCs, right? When you go to the gaming laptops and high-end video editing laptops and graphics laptops, you'll find that they're using a lot more. So due to the fact that a microprocessor runs very many tasks, a microcontroller only runs one specific task. So the other thing we need to look at when we're comparing a microcontroller and a microprocessor is the cost. So the cost of a microcontroller is low. Microcontrollers cost a few tens of dollars, $20, $40. Microprocessors can easily go for thousands and thousands of dollars. It depends on the kind of computer you're talking about. Let's say we want to build a computer that helps us in astrophysics, right? It's dealing with serious, heavy, complex calculations, right? Quantum computers. So you'll find that microprocessors cost more than microcontrollers. So let's look at the applications where are microcontrollers applied in embedded control, in embedded systems control. Microprocessors are used in day-to-day computers like desktops and laptops. So we will discuss more on this. So very many people confuse these two, a microprocessor and a microcontroller. The difference is in what one can do versus the other and other differences. So it's important to get this out of the way. So a microprocessor at one point is going to be seen in an embedded system. An embedded system can grow as big as it needs to, and it can shrink as much as it needs to. So I think we have understood that section very well. So let's look at something else interesting. Let's look at something else interesting. Let's look at an overview of the Atiny 85. So an Atiny 85 is nothing more, an Atiny 85 is nothing more than an 8-bit AVR microcontroller widely used in low-power embedded applications. It contains program memory, RAM, timers, ADC or analog to digital converter, and GPIO pins, or what we call general purpose input-output pins, on a single chip. Mark this what? On a single chip. So let's look at its pin out diagram. So it's a single chip, it's an IC, an integrated circuit. So we have all of these circuits, the ones labeled as program memory, RAM, timers, these are all different circuits, right? All squeezed into one chip. So let's start from there in the next section.